We had some initial result already maybe 5 years ago or something like that. But you know, sometimes it takes a long time before things come to the shape you want it, and I think that we now feel that we are ready. So now I had to, okay. So just with that said, I mean, in the group, we do a lot of federated learning activities. So for example, I'm interested in communication efficient algorithms, like compression error compensation. It's an area where we work with Dan, and you will hear maybe a little bit about this when Sarit Kirirat is talking in December. I'm also interested in resource aware and resource adaptive algorithms, so algorithms that kind of adjust the level of accuracy to the resources available. Another topic is the one you'll hear today, asynchronous algorithms. It's something we worked on for a long time. But I'm also interested in privacy preserving learning and learning on resource constrained system, be it memory, communication, whatever. And then taking kind of a whole picture about that. And I can give you many examples. So in the group, we have a lot of opportunities. If there's any PhD student or postdocs that would like to collaborate with us, we're always interested in new collaborations. It's just to reach out. So let's get into the talk. So I guess for you in federated learning, I don't really have to motivate the need for asynchronous algorithms. I mean, look at the picture to the left, you will see a synchronous system of federated learning type, say. You have a number of devices, and then say an edge device, and you want to do some type of learning on it. And maybe you want to do a simple gradient-based approach. And in a synchronous system then to the left, of course, the master, the Wi-Fi router here in this picture, would need to kind of query all the devices for gradients. They would need to compute with their own local databases. And the master would then need to wait until all of these had returned before executing the next iterate. And that is can of course be not only slow, but it can also be essentially complicated to implement. And note that we are very reliant on the speed of the slowest node, and we also very there's also reliance on node failure, risk for node failures. If we're very sensitive to node failures here. So on the right, on the other hand, you have a typical asynchronous iteration. So a device to the right has been free, let's say, so we can query it for a gradient. And then some minutes later, some seconds later, some iterates later, the device to the left has finished computing and returned the gradient. Now, based on some previous data that is now old or outdated, right? And the problem when we move from the synchronous picture to the left to the asynchronous picture to the right is then that it's kind of difficult to derive real-time guarantees and also to get some analytical insight. What works, what doesn't work, what works well, and etc. So you could chart this landscape in many ways. I try to do it in these two axes here. So on the y-axis, I have, say, the complexity of the iteration from linear to arbitrary nonlinear. And on the right, I have the assumption of how we execute this iteration. Synchronous to the left and totally asynchronous to the right. So like totally no coordination, right? So every work that we see here in this area, we could somehow place into this map. And if you look on machine learning today, I would say that a lot of the work on machine learning are the gray dots in the middle here. They consider non-linear iterations, typically gradient-based fixed point iterations for some gradient mappings, for example. And they assume some type of bounded asynchrony. But if you go back and look in the traditional literature, the influential work, of course, is the one by Bertsekas and Tsitsiklis, who then studied, let's say, two extremes. One was totally synchronous iterations, where there's no, where delays can go unbounded. And on the other hand, partial asynchronous algorithms, where we have bounded delays in terms of both how frequent each node must update and how old the information it can be that node uses, right? So that is partially synchronous iteration. I will come back to this a little bit later. But they made a great effort on working out that, mainly though for maximum norm contractions, a rather special type of iterations. It does have a lot of applications, but not really in the machine learning world, because it's very seldom that our iterations are maximum contractions. So what I would like to do, what our ambition has been with Hamid, is to try to fill the voids here. So that you can see, for example, there's a big uncharted territory between totally asynchronous and partially asynchronous algorithms. And also in many places, it's kind of not very systematic the way people have approached this. Typically, we rely on lengthy induction proofs. It's not easy to map back to get a good recipe for how to perform these convergence proofs. So I would then claim that the secret source of convergence analysis is POLIA plus POLIAC. So that's the combination you want. And what do I mean by POLIA plus POLIAC? Well, POLIA is, of course, POLIA, I mean, harder little wood. So you need, on the one hand, you need inequalities. And on the other hand, you need POLIAC. And POLIAC, in his book, as many of you know, made a fantastic work on systemizing a lot of convergence or sequence results that we can then map to like Lyapuno-like results for convergence of various sequences, right? So somehow we need both these sides. And of course, I chose POLIA and POLIAC because of the nearness in names, but today typically would go to Nesterov's book, perhaps, or maybe Amir Beck's book, to find good inequalities, because these are people that made a really nice work of systemizing the type of inequalities you have for convex, strongly convex function, for proximal mappings, etc. So in this work, what we would like to do is to contribute to the POLIAC side of the picture. So we'd mainly like to show new sequence results that we can then work towards in order to get convergence guarantees for these more complicated iterations. So that's the ambition of this talk, and also, of course, we will also show that these inequalities these sequence results that we derive allow you to shorten and streamline proofs, but also allow you to get better result than what was previously known. And we believe that mainly that is because mainly that we know where to aim for. So our induction proofs don't search just for convergence, but we actually search to maximize the quantities that in the end will determine convergence constant and convergence rates for these iterations. All right. So before going into that main part, I just would like to make a few brief words about asynchrony and information delays. What is the relation, etc. Because the sequence result, they will be formulated mainly in terms of delayed iterations. Okay, so we need to make a little bit of that mapping. And I will come back to that later when we talk about applications. I will only give two applications. One is on proximal incremental aggregate gradient descent, something that is quite similar to what the federated learning system would work like. And the other one is to show how these sequence results can be used for Bertsekas, unified results by Bertsekas and Tsitsiklis. And actually, although I will not show it, also reach out through between the totally and partially asynchronous algorithms. So that's kind of the roadmap for the talk. So let's go on and let's discuss a little bit about the models of asynchrony. So a good thing to think about is like a fixed point iteration. You can think T of x is x minus gamma gradient of x, so like a gradient iteration, for example. But take any fixed point iteration. And now we'd like to parallelize this one. So we can do it in the simple way that we evaluate each component of x in parallel with a mapping on the right-hand side, component-wise, let's say. So we have this update. So bracket here means component of a big vector, the ith component. And that's the corresponding entry of the mapping, let's say, on the right. And if we now want to do this implementation as asynchronous, we would need to let each core or each node responsible for updating such a component to work at its own pace. And what happens then is typically that the components available to node I may not match the components of X available to node J due to the fact that nodes operate in this asynchronous way, either over a network or writing back to shared memory without any local, say, synchronization, global synchronization, sorry. So we get this type of inconsistency here that then manifests itself as delays, as we will see. And in general, I would also like to say that it's quite difficult to bookkeep this kind of read-write events in a distributed system and map them back to to physical time. So that is something that we will give in. We'll give up on that mapping to physical time today, and we'll do what is standard practice. We will view time mainly as an ordering of events. So that ordering could either be read events or write events. And actually, it is kind of critical if you want to have a good model, a faithful model of reality, whether or not you let time be decided by the read event or write events in the system. But let's now look at it as the update events, like write events.
Is it okay we have one question before we move on?
Of course.
And is it okay that I interrupt between to allow people to ask questions?
To me, it's fine. It's up to Dan, and I mean, I'm totally fine.
Okay. So we have one question from Konstantin.
Thank you. Do you hear me?
Yes, I hear you.
Okay, yeah, thank you. So I am new for the world of asynchronous algorithms. But in the taxonomy presented several slides ago, when in x-axis it was a completely synchronous algorithm, completely asynchronous algorithm. Does it exist some algorithms which are problem dependent in such way we don't know when synchronization will happen in advance? So the algorithms by itself defines where synchronization is needed.
Today I will talk about the analysis of algorithms mainly, but we are also interested, and we're actually working on that now, adaptive algorithms that would adapt to the delay distribution. So in that way, they would, if the delay abounded, they would benefit from that, and if the delay grow very large, they would still guarantee convergence. Is that an answer to your question?
Okay, thank you. Yeah, and one question regarding previous slides. So should xk be indexed by the client as well? Because like in the previous slide, as I understand, the clients will do this construction, fixed point iterations, they handle different iterates.
So should k be dependent? What was
so what is a k? What is a k? What is k? Is it index of the client or it is number of iterations?
Now, k here is iteration index, so it's time, let's say.
Okay.
So in this slide here, I would like to have synchronous time. So every time at every iteration k, I evaluate that mapping in parallel, and when all nodes, let's say parallel nodes, have evaluated that part of the mapping and written back to memory, then we increase the iterate counter. So that's
okay. So in that slides, the clients handle the same xk.
Everybody has the same xk, yeah.
Okay,
slide. So in the more general setting, though, now if I let the time, so the iterates tick up, my iterate counter tick up whenever there's a write event. I mean, whenever a node updates it, completes a computation, we will get an iteration on the following form. So now I have sets calligraphic ki here. These are the set of indices at which node I doesn't update. So the ith component of my big vector, of course, it's unaltered if node I doesn't update. So that's the second case. And if node I updates, it evaluates its part of the mapping, but now it has access to delayed versions of the different components from the other m nodes here. So we get an iteration of that form. So you can see here, what we have is an iteration with information delays. And I will come back to this and discuss in more details later, but I just wanted to show for now that the way we deal with asynchrony is that we let time tick whenever node updates, and in that way we get delays on the right hand side. So we get delayed iterations. And in this talk, I will just allow delays to be arbitrarily varying. So they might be bounded or unbounded. We'll go into that later, but they will be allowed to vary arbitrarily. And of course, you may want to do more, but this is what we do here. So let me talk then about this secret sauce of convergence analysis. So I would like to talk a little bit about inequalities and sequence results. And before showing the actual results that we have proposed in our paper, I would like to do something very simple. I would like to start with just unconstrained minimization of a convex loss function. And I would just like to look at gradient descent iterations. So of course, everybody here knows how and when these iterates converge. But let's go and see how we prove it in detail. And I want to show that in order to show or motivate why we extend the theory in the way we do. Okay. So if F is mu strongly convex and L smooth, typically what you do is that you look at the distance between iterates and the optimum. And on the right, we just plugged in the gradient iteration. You expand, so nothing happens here. And then you deal with the middle term by this inequality on the bottom, so that you can find in, for example, the book by Nesterov. And that's kind of the iterate relationship. So that's the inequalities. That's the massaging of the iterate relationship. And we get that kind of inequality. So that's the PIAG, the inequality part. So the PIAG part, the convergence, the sequence result, would be something like this. Of course, now it's very trivial. It's a contraction. In addition, it has another disturbance, WK. So VK and WK are positive sequences, so non-negative sequences. And the convergence result could say that if R is positive and Q is between 0 and 1, then VK will decay. So there will be a contraction in VK. And of course, the proof of that is trivial, right? So if R is positive, WK is positive, I can just drop the term on the right-hand side. And then I can just iterate this inequality to find the conclusion. And now if we go back on the previous slide and look at the iterate relationship we derived, it just maps back to this. And we have VK as a distance to the optimizer and WK as the gradient norm squared. And now I can map back to this sequence result and immediately get the result about convergence. So let's see how it could look when we don't have strong convexity. When we don't have strong convexity, we think it's natural to look at a result like this. We'll consider non-negative sequences, VK, WK, and XK, satisfying this inequality. And then say if R is non-negative, then the sum of XL from 1 to K is smaller than V0. And in addition, if XK is decreasing, then XK is smaller than V0 over K. And that proof is also trivial. We just drop the last term, like we did in the previous result. We just sum across times. And then notice that this is telescoping going on, so we can cancel some VK terms on the left and right of the inequality, and we'd end up with inequality here at the bottom. And of course, on the left, I can lower bound this quantity by dropping VK. So I essentially get the sum result up here after relabeling of the iterates. And the final claim is also trivial when XK is decreasing, right? So if you now go back to inequalities, I will not redo that work here. In absence of strong convexity, typically you would come after application of 2-3 inequalities, you would come to an iterate relationship in the middle here. And again, you can see that maps perfectly to the sequence result above, where VK is XK minus X star, WK as before, gradient norm squared, and then I've introduced this other term, XK as f of XK plus 1 minus F star. And now I can go back and immediately map what I have onto that sequence result. I will get the standard 1 over K convergence for gradient descent on L smooth convex functions. So that's the basic thing, right? So what about now in asynchronous systems? In asynchronous systems, we have in our updates will depend on the recent history of the iterates. I mean the delayed iterates. So instead of the first type of inequality we have on the left, we propose that we should better understand the blue inequality here on the right. And now you can see it has delayed terms, delayed versions of VK ending up in the right hand side, and they're bad. I mean, they are adding, say, to the right hand side. They're not helping us in any way, and but that's the inequality we would like to understand. And corresponding to the second type of sequence result, we'd like to study an extension to the right. So again, to the right now, you can see that you have disturbance terms of WL here, adding to the right-hand side in the wrong way. So you can no longer immediately drop those terms and sum. Okay, so these are the two type of sequence results that we say that we should better understand. And once we know that, we have a good path for analyzing asynchronous iterations. So now let's move on. Let's see what we can do about this. So here's the first result you'll find in our paper. It actually considers just the sequence that I showed you. So it says that VK be a non-negative sequence satisfying this type of iterative relationship below. And it assumes that tau k, the information delay, is bounded, and that bound will throughout this talk be denoted tau. And it also assumes that p plus k is smaller than 1. And if so, it says that we still have linear convergence or contraction, but the constant rho will no longer be like in the delay-free case. Delay-free case actually is p plus q in this formulation. But the convergence constant, contraction modulus, will shrink, will increase with tau. So as tau grows large, this rho will go to 1. And in the limit, we won't have any convergence at all, any contraction at all. And if tau equals 0, you'll actually recover the exact convergence constant we had in the delay-free case. Note that VK also appears in this max here, this max term. That's why P plus K correspond to what was Q. P plus Q correspond to what was Q in the previous slide. So how do you show this result? I mean, this result is actually not very difficult to show. Here's a very compact version of this proof, and I don't expect that you follow perfectly now, but I just want to show you that it's not too difficult. So the proof starts by noting that since p plus q is smaller than 1, p plus q to the minus tau over tau plus 1 is greater than 1. I divide by something that is smaller than 1. And the quantity that I will need in my convergence proof later is q plus p times rho to the minus tau. So let's see what we can say about that. So now I just plug in the definition of rho from the previous slide in this expression. And then instead of multiplying q by 1, I multiply it with the larger term that we just derived, p plus q to the minus tau over tau plus 1. So I have that bound. And then you can now manipulate this, adding 1 to the exponent essentially, and just doing simple math. And you'll see that that is actually rho itself. So we go back to rho itself. So now I have this kind of small result, and we can proceed by induction. So the hypothesis that you have, convergence hypothesis, that holds for k equals 0. That's simple to see. And then we can assume that it holds for every k up to some k bar, in which case v of k bar plus 1 satisfies this inequality. And here I actually have gone from tau k bar minus tau k to k bar minus tau. I'm just adding more non-negative terms here and taking max from a larger set. And that's why I can do that. And then I will use the conclusion, because under the induction hypothesis, I can bound both v of k bar and vl by rho to the corresponding coefficient times v0. So that's what I plug in. And then I pull out v0 and rho to the k bar to the left. And you can see now I have exactly this term that I was manipulating above. So that inside the parentheses here, mostly on the right, that's rho itself. So this is smaller than rho k bar plus 1 times v0, which means that the induction hypothesis holds also, holds for k bar plus 1. And therefore our claim holds for all k. So you can see it's not super difficult, and it's techniques that you know about, essentially. So let's move on and study the same iteration, but instead let the delay tend to infinity. So of course, I cannot immediately let the delay tend to infinity. I have to somehow ensure that there are updates happening in the system. So I will impose the constraint that as k goes to infinity, k minus tau k will also tend to infinity. And then we can show that if p plus q is smaller than 1, vk will converge asymptotically to 0. However, in this case, we cannot really provide a rate. We can just provide that it will eventually prove that it will eventually converge. So if you read our paper, there is a framework that we actually that's been proposed in the actual neural network literature called mu stability that we use to also get rates for classes of unbounded delay. I'm not going to cover it here. I don't think we have time enough. I want to move over to the second type of inequality. So recall the second type of inequality had 3 sequences: vk, wk, and xk. They're all negative, non-negative. And we said that we had to satisfy an iterate relationship like so. And then our result then says if pk and rk are non-negative sequences, and tau k is bounded by tau for all tau, if some pk plus l from L equals 0 to tau is smaller than rk for every k, then we get that v capital K is smaller than v0, and that sum of xk that we studied earlier is smaller than v0.
One quick question, if we have.
Yes, of course.
So, question by Kumar. Can you ask the question?
Hi, can you hear me?
Yes, perfectly.
Yeah, I was curious if you can also show results for average bounded delay rather than the maximum delay being bounded, because that would allow you some generalization over what you have.
Yeah, we have not worked on that. I think there are some results, maybe from the group by Wu Tao Yin on this. Although I think you have to add something more about the distribution of delays, not only the average.
Yeah, I think I remember seeing such a paper, and that's why I was curious how your results compare to theirs.
Yeah, so it's difficult to say. I mean, I don't think they're not directly comparable, these results. So I don't have a good answer. I think we need to sit down and work it out.
Oh, okay, sounds good. Thanks.
Thank you. All right, so let me show you a sketch for the proof of this type of result. So now for ease of notation, because note here that we'll only look on this sequence from 0 and on, from k equals 0 and on. But WL is delayed. So actually, if we don't do anything here, we'll get W minus 1, W minus 2, etc. So for convenience, we just define them to be 0 for k smaller than 1. And then we do just as in the delay-free case, we sum over k, and we'll get the quantity that you see here. And then we will use that pk and wl are non-negative, so I can bound over a larger space. I can add some terms to get up to tau, so something that is not time dependent. So the index here is not time dependent, k minus tau instead of k minus tau k. And then what we do next is actually, let's say, standard manipulations. We reorder terms, we relabel iterates, etc. And doing so here gives us a sequence result on this. And now we essentially back on the delay-free case. So if now rk minus sum of pk plus l, if that is non-negative, then I can drop that right-hand side and I get the result I do in the delay-free case. And that's essentially the conditions of this lemma. So there is actually a more advanced lemma that we can also use to get linear convergence for these type of iterations. And we have it here only with constant Q, P, and R. But you see we have Q, P, and R here. So there can actually be a contraction in terms of Q. And this one is a little bit more tricky to prove because you have to do more careful bookkeeping and bounding, etc. But it essentially shows that if 2 tau plus 1 is smaller than a certain quantity here, we'll still get linear convergence. And we still get some type of bounding of the sum of xk. So we get linear convergence in V and some type of weighted bounding of the x case. And the interpretation of that kind of result is that the linear rate that you get in an undelayed case is somehow robust to small delays. And also this result, if you go in and put tau 0 here, we can see that it recovers the delay-free result. So I think it's too many details to kind of just push through here on the slide and in a virtual talk like this. So I really would like to refer you to the paper that Hamid and I put out. And now I'd like to move on then to show a few applications of these sequence results. And the first one is for proximal incremental aggregate gradient descent method. So usually that method is used for in say a parameter server setting. So it's not perfectly mapping onto a federated learning system, right? But let us study that because that's what we do in the paper, and I hadn't had time to work out something for exactly that matches to federated learning. But typically, a parallel implementation of this would look something like that. So of course we have some type of empirical loss. Each node here, worker node, has access to his or her own data set and can compute the gradients with respect to that, the loss in that data set. What they do is they query the master for an iterate x, and then they compute the gradients, and then they return those gradients. And master, on the other hand, maintains an average gradient where it uses the most recent component that it has received from every node in the system. And then it takes updates with using that gradient, let's say. And the proximal version of this is a little bit, not very much, a little bit more complex. I will show it in the next slide. But it tries then to minimize f of x plus r of x. And f of x is some empirical loss, and r of x is a regularizer, which is a proper closed and convex. And the algorithm would typically work like then, as I mentioned, that workers compute, say, incremental gradients with respect to that subset of data, and the master maintains this aggregate of the most recent gradients of each data point, of worker rather, that's GK. And now you can see the delays enter because we have retrieved them from workers at different points in time, and that those workers had access to different versions of the decision vector. Note, however, here they all have the same. They all retrieve a synchronized version of the X from the master. So each node I has access to the same. Each node I has the full vector where each component has the same delay OH. And then the master then with this GK takes a proc step, what you see below. So that's how the algorithm works. And I'm not going to show the detailed proof that we have for proximal IAG, but I want to show it for IAG. So I want to remove the prox term now. And in that case, the proximal step just becomes the gradient step. And for this case, it's straightforward to show this type of 1/k convergence, provided that each Fi is L smooth, and we pick a step size that is inversely proportional to tau squared. So tau is a maximum delay squared. And such a proof, I mean, how would you prove such a thing? Well, you would just apply L smoothness and convexity for each component function. So the first inequality I show here, that's just L smoothness of Fi. Sorry, that should be small Fi. I have lost a sub I on the two first F's here. So that one is just L smoothness of F sub I, and then the second inequality comes from convexity of Fi. that allows me to express the bound the right-hand side in terms of fi at x star. Now we sum over the component functions. So on the left, when I sum over all component functions, I will get capital F. So the empirical loss, let's say. And on the right-hand side, I will first get f of x star. And then I sum all this nabla gradient of fi. That will give me the g vector, etc. And g vector is just, I can rewrite it in terms of the iterates. So I just plug in the expression for the gradient updates, and I solve that, isolate g from that expression, and that's what you see in the second step in blue. So I just replace g by its relation to the gradient update. And then I have this inner product, which is this type of three-term equality. I can just expand it, and I end up in the last equality. And now the only thing I have annoying, so now I worked away tau k from the middle, but I still have this bound on the left, where I have the distance between xk plus 1 and xk minus tau ki, and that is a little bit annoying. So that one we also have to bound. And that bound, typically what we have been doing and most other people have been doing, is to bound that distance by rewriting it as the incremental sum of incremental distances between xj and xj plus 1, where j is now goes from tau k minus tau ki to k. And then the final, once we just rewrote it, we can bound it using Jensen's inequality, and we get the bound on the right. And then if I plug everything together, I end up with an iterate relationship like this. And actually, if you remember what we had for the gradient descent, we have the same terms. The terms on the left are the same as the delay-free gradient descent. The first term on the right is the same as the delay-free gradient. And then the final terms, have this form that we're looking for now. And we have pk and rk. And I just plug in essentially the relationship, saying that I should be able to drop these terms when I sum over time, and that gives me the claim. So that gives me this 1 over tau squared, essentially step size, because there are tau plus 1 components here that together needs to be smaller than 1. So essentially, you can analyze a rather, say, complex algorithm using these sequence results in a rather straightforward way. So I would argue that this proof that we have is short and streamlined, but it's not optimal. I mean, it's not optimal to use. You don't need to have a 1 over tau squared step size. But the problem is not the sequence result. The problem is really the iterate relationship that we derived. So as the next few slides, I will show you that this proximal IAG, and thus this IAG that we analyzed, converges for step sizes that are smaller than 1 over L tau plus 1s. They are just inversely proportional to tau, not inversely proportional to tau squared. So that's a big leap, let's say. And what we need to do to do that is first a lemma about an iterate relationship. And actually, I don't think you need to. We can look at the lemma, the final line of the lemma, in a little bit. But what you should note is that it essentially combines two different iterate relationships. One is more or less a proximal version of the one I derived in the previous slide, and the second one is a version of an iterate relationship that I think Van Lee and co-authors used in their paper. And this was not so easy. So this actually Hamid's brainchild to combine these two iterate relationships with a time varying weight, alpha k, which is k plus alpha 0. And by doing that, you end up with the iterate relationship below. And that is again captured exactly. It actually has exact form from previously. But there is no xk here. Xk, which used to be the distance between xk and x star, those are gone away. We had actually included them in vk here. So you only have these w terms in the iteration. And then we can apply the sequence result. And we'll find out that for every step size smaller than, for every non-negative step size smaller than 1 of L, 2 tau plus 1, this will converge, these iterations will converge, and they will converge essentially order 1 over k. And while the first lemma here was a little bit difficult to derive, the second one is more or less an immediate consequence of the sequence result. And actually, I mentioned earlier that this sequence result can use either xk or vk as performance measure, and it actually uses vk, puts all the performance in the vk sequence. So that's that result, and this one is actually better than existing results. So actually, there are very few results for this proximal incremental aggregate gradient in absence of strong convexity. So Sun and co-authors from at NeurIPS 2019 actually provided a 1 over k rate, but they were not really explicit about the constants. And Huang and others have a paper now on arXiv where they prove that the Sun analysis yields a rate that is proportional to tau to the power of 3, L to the power of 2. So kind of heavy dependence on both the delay and Lipschitz constants. While our results here have let's say linear dependence on both tau and L. And if you read the paper that we have out, we have also result for strong convexity that gives the same linear dependence on kappa, so the condition number, and the maximum delay as the best result in the literature. So Van Lee and others from Siam in 2018. But our results allow for larger step sizes and provides a tighter convergence bound, and it's also proven under less restrictive assumptions. So I mean, yeah. With that, I'd like to argue that these sequence results are not only like easy to apply, but they can also give you very, very tight results. And I want to give one more application before concluding, and that is these partially and totally asynchronous iterations. So if you've read the book by Bertsekas and Tsitsiklis, you know it's a super nice book with these results. But the two results are shown using quite different techniques. It's not obvious what's the Lyapuno function. It's more like a geometric proof, and convergence rate are not so explicit, let's say. So what we wanted to see if we can have a Lyapuno approach that allow us to more or less analyze totally asynchronous and everything in between in one framework. So that's what we are trying to do here, and I will be brief here, so there won't be any proof. I'll just walk you through roughly what we have here. So again, it's a little bit what I showed before. So we have a product space of d-dimensional vectors, and I would like to find a fixed point of a mapping that then maps from this product space to the product space. So you can think about m nodes, each having a vector of length d, right? And then they update what exactly the way we mentioned earlier when I introduced the delayed iterations. So that's the iteration we'd like to analyze, and we would like to make this limitation I also mentioned in an early slide, that T is a pseudo contraction with respect to the block maximum norm. So pseudo contractions, it contracts the distance from X star, and the next iterate kind of decreases, and it decreases in this weird norm if you haven't seen it before. So the block maximum, weighted block maximum norm, I can choose an arbitrary norm for each mode, for each node. So each node I can have an arbitrary node. That's with the norm I sign in the bottom. And then I take the weighted maximum of these norms among them m nodes, and that gives me this block norm. And we assume that this mapping T here is a contraction with respect to that norm, and that's essentially an assumption that's also made in Bertsekas and Tsitsiklis. So we choose to define the weighted norm a little bit different, but that's just for ease of presentation. So for these kind of systems, this is the abstraction this is the graphical model you can have of it. So I have a number of nodes, M nodes, they all access to their own data. They all store their own, say, subvectors xi, and then they update these. So they query the remaining part of the subvector from other nodes, and then they use their own data set to define TI and perform the update right to the local memory. And whenever another node needs that part of the subvector, you can just query it and get a delayed version of it back. So that's kind of the system that you want to analyze. And then here we have exactly that kind of asynchronous iteration I talked about earlier. So the clock now will tick whenever any node updates. So I will have sets calligraphic ki here, whenever node I, that explains when node I updates. And I've used SIJK here. That's the time at which the subcomponent xj available to node I at time key k was computed. So to map it back to the delay, the tau ijk we've seen before, that is k minus sijk. So tau ijk, k minus sijk is the information delay from j to I at time k. So now we have an iteration on this form, and we would like to see under what condition it converges. So then I think maybe the key result from this part of the paper is to show that if T is a pseudo contraction with respect to the block maximum norm with modulus C, then the iterates generated by such an asynchronous iteration satisfy a relationship like such. So Vk plus 1 is smaller than C times max over VL, where L goes from K down to K minus tau K. So what is nice with that is that that's a single iterate relationship. It doesn't matter here if tau K is bounded or go to infinity. They always, that is kind of the nature of this asynchronous iterate update on a block maximum norm. But you see in the sequence results, you see that this matches perfectly with the sequence result, the first kind of sequence results that we derived. So we can now then go back to Bertsekas and Tsitsiklys and look at, say, the total asynchronous version. And that assumes that all ki are infinite subsets of n0. So that means that each node updates infinitely many times over infinite time then. And then it has this, which is this bound on delay that we also see on the previous slide. So k minus tau k should go to infinity as k goes to infinity. It should satisfy that kind of relationship. And under those conditions, everything for the second sequence lemma that we showed in the talk is satisfied. So we can immediately conclude that if T is a pseudo-contractive mapping with respect to the block maximum norm, then the sequence generated by a totally synchronous iteration converges asymptotically to the unique fixed point. And if we look at the partially asynchronous iterations in Bertsekas and Tsitsiklys, what they say is that there should exist bounds B, capital B, and capital D, so that at least one of the set I show here should belong to Ki, meaning that each node will update at least every B iterations, will execute at least one iteration every B iterations. And whenever, the second point is whenever node updates, the delay on the information cannot be more than capital D. So that's the second point. And then the third point says that node I should use the latest version of its own updates. It should actually take the time, take the iterate, it has a time k when it updates at time k. So that's the three conditions. And what these result in is actually a delay bound of B plus D if you turn it back to the delayed iterations framework. So you have capital B plus capital D. So again, we can go back to the first sequence result that we have and immediately get not only convergence, but also quantify the convergence factor of these partially synchronous iterations in terms of B and D. So, and again, this is again an immediate consequence of the sequence result. And you have a clear quantification of how the iterations slow down as the iterations become more and more, say, uncontrolled and asynchronous. If you hadn't had enough of these, if you want to read the paper, you will see one interesting thing I think in the paper is this fact that we have convergence time bound also for totally asynchronous iterations. If you put a little bit more assumptions on how the delays can tend to infinity, you can actually get rates. And we also have sharper convergence bound for the AROC framework. So that's from the group of Wu Tao Yin. That's a really nice framework that captures a lot of things we might want to do, like coordinate update methods, ADMM, etc. So I encourage you to look at that. It also, of course, all the details, a lot of references, and perhaps a much better way of expressing this than what I've been managing to do today. So I think I'm ready to conclude. What I wanted to remember from today is what I call the secret sauce of convergence analysis. On the one hand, inequalities that end up with iterate relationships, and on the other hand, sequence results. So somehow the inequalities are kind of the Lego blocks that we use, while sequence result is more like a map or a model. We know where to head for, so we know how to manipulate, or we have an idea of how to manipulate our iterates to conclude what we want to conclude. And I present a number of new sequence results for synchronous iterations. So actually some of them we presented quite some time ago, but the latest ones are quite refined versions of what we have had in earlier papers. And I think and I hope I could show that they're both simple and powerful. So simple in the sense that, you know, we can show IAG analysis convergence in like 2 slides, which is something like 10 lines. And also that they're powerful. So now I didn't show you all the details, but if you read the paper, you will see that we can use these sequence results to get, in a transparent way, very powerful convergence results. And I think that's essentially it. You know, there are many extensions that you could potentially work out here, and I'm sure that these results can be further improved, so nothing is final. And I also want to say that we are currently working, I got some questions about this, but we are currently working on transforming this from analysis to design. So we're looking into how can we do delay adaptive step sizes, how can we do algorithms that work better in phase asynchrony. I think, Dan, that's all I wanted to say.
Okay, then thank you for the interesting talk. So if anyone wants to ask some question, I'll allow to unmute themselves and ask directly. So you can unmute yourself from your side and ask the question.
I'd like to start if I can. So all the results presented here are for individual functions, like each worker has its own data, right?
Yes.
Do you think it is possible to get better results by assuming that they all sample from the same distribution, some stochastic gradients?
I mean, yes, it should be better because I think we have stronger inequalities to work with in that case, right? So we should be able to. I'm not sure if the sequence results need to be updated, but we should be able to get better results because we have stronger inequalities to work with. Yeah. So we didn't look at it, or at least I didn't look at it. So I don't have a better answer. No more questions?
All right, so I guess, yeah, so there's no more questions. So thank you again for the
Right.
talk. And I'm not sure we asked before, but we hope we have your consent to post the talk on our YouTube channel, right?
Yeah.
Okay, thank you, and yeah, have a nice day.
All right, thanks. Bye.
Thank you for the presentation.
Thanks.